So welcome everybody and good morning. I'm delighted to be here and a little bit perplexed. This has been quite a difficult talk for me to prepare. So I'm a lecturer, an assistant professor in the School of Computing. So ask me to talk for several hours on data visualization theory or basic operating system principles or introduction to computer programming, no problem at all. Ask my students. Ask me to give a talk on my research interests, I can do that at the drop of a hat. You can get me up in front of a crowd and I can talk about computer vision, about analytics, and about the variety of research projects that I do. However, this talk is not that. This talk is more looking at stories around how Python is used within my work, and how Python is used, particularly at DCU, in both the undergraduate and the master's programs. I'm not going to necessarily share any new insights into Python itself. Most of you probably know more or have forgotten more than I have ever known, although I have had a very long experience with using Python. So the talk today will mostly talk about my story and experiences, and then we'll look at how Python is used within research and education. So let's start with who I am. So the standard bio tells you I'm an assistant professor at Dublin City University in the School of Computing. I'm also the chair of our brand new Bachelor of Science degree majoring in data science, which is a new degree. They're in their second year. And that is an interesting one, I think, to this context because it's a mixture of computer programming. They learn Python with the undergraduate CS students, statistics and mathematics, and then data analytics or domain knowledge. I'm also what's known as a funded investigator in the Insight Centre for Data Analytics. This is a Science Foundation Ireland funded research centre. It's very large. Some numbers up there for those of you that like to see the statistics. And it's spread across 4 universities, major universities in Ireland. And I'm part of a much larger research team there, and they've contributed in various ways to this talk. So a little bit about my research interests. A simplistic way that I've used in the past to describe what I do is that I teach computers to see. So I do some work in computer vision, and my main interest is really in how you can get better information out of visual documents. So images, photographs, video, and you want to track objects or identify trends, recognise antisocial behaviour. I have European projects looking at driver assistance systems, so being able to track cars or understand what sort of situation a vehicle is getting into. And all of that kind of comes under that heading. So I take pixels, the numbers that are inherent in digital imagery, and I turn that into semantic terms. Part of that is really I help people find information. So turning that into semantic terms and then being able to put it all together to solve problems is what drives a lot of my research work. I also work with Croke Park Stadium. So those of you that are in Dublin will know that very well, or in Ireland, and it's perhaps a slightly odd professional research relationship. So this is a project called Smart Stadium, and it's a collaboration between DCU, Croke Park, Intel and Microsoft. So I'll be using some examples from that project to illustrate how we use Python in our work. So to address the elephant, or perhaps the kangaroo in the room, yes, the accent is not local. I am from Australia, and the question is often asked, well, how did you end up in Dublin? So it's a slightly roundabout journey. I left Australia to take up a postdoctoral position in Pisa in Italy, and I followed that up by a postdoctoral position in Leipzig in Germany. At which point the plan was to return to Australia and work as a researcher there, but I looked around and I ended up in England, which isn't quite Australia, but I was there for a number of years at the Open University doing research in various projects. That came to an end, and again I thought maybe it's time to go back to the Southern Hemisphere where they have normal summers, and I can understand what people are saying when they talk. But I had the opportunity to come instead to Dublin. In particular, I was driven to work with Professor Alan Smeaton, who some of you may know. I can see a few faces here who are from DCU. You've probably been taught by Alan, who's quite a well-known name in information retrieval, particularly in video analytics. And I thought, well, that would be a nice thing to come. That was 7 years ago. So I've kind of become a bit of a fixture in that time. So I've enjoyed life in Ireland. It's actually quite similar to Australia in many ways. And I really found fantastic research opportunities in Ireland, and particularly with the research centres. And that's led to me doing all sorts of odd bits of outreach. So the slide here shows one of the scientist apprentice books from 2 years ago. You might know that they're being released again now. I can highly recommend them, particularly if you've got children. You can pick them up, I think, from SuperValue or Tesco's or something like that. And these were produced by Science Foundation Ireland to get researchers to describe their work for primary school students. So I'm featured in that one, so a publication that I'm particularly proud of as an academic. I also do a lot of work with things like Girls Hack Ireland, which was looking to encourage particularly teenage girls to think about STEM as a possible career option. There are many fantastic initiatives that do this type of thing, and I won't name them all because there's too many to consider. But I think one of the differences we found with Girls Hack Ireland was talking to the parents and guardians of not just female high school students, but also male. There's a lot of misunderstanding about what it means to be in computing. We're all tech people, and the wider public has a particular view of what that looks like. But I can tell you that standing up here on the stage, that stereotype is completely untrue. But communicating that to other people and getting them to see that computer programming, that technology, that maths is an exciting, a credible, a rewarding career choice. I think that's a responsibility that we all have, and it's something that we do a lot as part of the research centres. So I guess the final thing is to give you some of my credentials, so to speak. Why am I talking at a Python conference? Well, I was introduced to Python way back in 1999, so Python 1.5.2, for those of you that remember using that. And it was a student project, and the challenge was to take a formal program specification, so mathematically specified program in a language called Object-Z, and try to create an automatic animation program. So it would take the mathematical input and automatically generate a Python code that would evaluate that specification for correctness and completeness. This was very interesting. Python probably wasn't the best choice, because one of the things about formal specifications is a lot of it is about the type of the variable, and as a non-typing language, I essentially had to fudge type checking in Python, which at the conclusion of the project, my supervisors and I looked at each other and went, yeah, maybe not the best choice. But it was a lot of fun, and I learned a lot about the language. I went on to use it for all sorts of odd projects as I continued through my research degree and through the work I was doing. So search systems for online presentations. Some of my PhD work was on automatic annotation of microscopy images, so looking at pancreas cells from mice, and writing Python programs to be able to derive labels for certain regions. So I used things like WX Windows to create a standalone GUI that you could scribble on to identify regions and colours. I did a lot of work with image similarity and indexing, so looking at very, very large collections of photographs and trying to cluster them using various libraries that were coming out in feature extraction or efficient indexing, that type of thing. When I came to Dublin, I was doing a lot of work on surveillance video search. So again, I reached for Python to build a quick interface to be able to search this as a client-server framework. In 2014, I discovered IPython notebooks and pandas, and that had quite an impact. One of the things I'd always liked about Python was the fact that you could fire up an interpreter in the terminal and quickly check, quickly figure out what was the best setting for something, or did you have your code correct. So the appearance, to me, of the IPython notebooks was a fabulous way of suddenly having a legitimate reason for having a scratch pad and being able to just check small bits of code and pull stuff together. So as part of that, I started to do more work on using Python for data analytics. I ran various internal courses for the chemists to try and convince them to ditch MATLAB and move to Python, and started to do more work on how Python could be used to do considerable data analytics in a very structured way and looking at visualization. And we've ended up here where suddenly I'm teaching data analytics and data management, and my tool of choice is often Python. So I teach that to the master's students in DCU for their data analytics project. So one of the things I often do as a lecturer, because obviously it can get a bit boring to sit and listen to me talk for a few hours, is to get some input from the audience. So can I ask everyone to pull out your mobile phones, which normally I'd be telling you to put away, and if you go to menti.com and hope that the technology gods are smiling, here we go. So if you open up menti.com, it'll ask you for a 6-digit code. So if you enter that code in, I've got 2 fairly simple questions for you. I'd like to know what your first programming language was. And I couldn't put every single possible option. I did look at a few other surveys to see what sort of options they gave. So I picked a few of what I think are the fairly obvious ones for the first question. And then the second question is, if you answer other, it's a word cloud, and I'm going to get you to put in what your first language actually was. So let me double check this is actually working. Menti.com 2678339. Okay, so 71, 72, a lot of people here. Okay, so let's have a look and see what's that looking like. Okay, so that's interesting. In this audience, overwhelmingly we've got other and either C or C++ as the very first programming language. Now, I know that sometimes that could be a slightly tricky question, and maybe you wrote your first program in something else, but you were formally taught a particular language. I don't really mind. Whichever one you consider to be your spiritual home, the first language that you were taught in. So I'll just give that another couple of seconds. But we have pretty much, well, depending on what the other throws up, maybe I've forgotten something really, really obvious like, oh, I don't know, Go or Erlang or something. It's looking like C, C++ and other. So that's kind of expected, right? A lot of people, that's what the universities in particular would start with. C is for serious programmers. It gives you all the information you need, you compile it, you can pull the stuff together. So that seems to be slowing down to a trickle, so I will move it on to the other question. So if you answered other, what was the language? Now, my first programming language was Smalltalk. So if I do that, Smalltalk, submit. Okay. So I think they picked Smalltalk when I was studying because it's object-oriented. So the good thing about learning Smalltalk first is I got a really, really clear introduction in my head about object-oriented structures before I moved on to anything else. Now, I went to university to study chemistry. I liked messing around in the labs. I thought chemistry would be what I wanted to do. I discovered that studying chemistry wasn't as much fun. And I picked up an introduction to computing subject because I didn't know anything about computers. I didn't even know how to use one of these. And I really enjoyed it. I loved the fact that I could make computers do things and that we were programming noughts and crosses and making games and playing around with stuff. So I took more and more computing subjects and fewer chemistry subjects and ended up with a degree in software engineering. So my first one was Smalltalk. So let's have a look and see here. Pascal, of course, I should have thought of that one. Yes, so that's another really common one. And Basic or Visual Basic, there's a few common ones in there. I'm not quite sure how Python and Java got in as other. Anyway, someone just wants them to win. There's a few in there I've never heard of. So the MIRC scripting language. Oh, that was for the IRC chat channels. Yes, of course, that makes sense. Perl and MATLAB, yeah, of course, they're big ones as well. Beginner Get to Train, welcome, fantastic to have you here. Okay, so hopefully you can see from that there really is a variety of pathways that people come to Python. Now, I'm assuming most of you have some experience with Python, that's why you're here, so I didn't ask about that as part of it. But there were fewer of you that started with Python as a programming language, as your first language than I thought. right? Because that's really what a lot of the institutions are moving towards these days. So you've heard that we've got a new leaving certificate, Computing in Ireland. The undergraduate degrees at DCU moved to Python about 3 or 4 years ago. So that's what our students would get introduced to first. So I suspect that if we did that graph again in, say, 3-4 years' time, it might start to shift slightly more to the Python side. So thank you for providing that, and given that I do lecture in data protection and privacy, I will pledge that there is no personal information collected from that, and I will delete the results of that at the end of the day when they are no longer required. So... Okay, so what I want to look at now is really just some examples of how Python gets used where I'm wearing different hats. So I'm a researcher, I'm a software engineer, so that means I sometimes approach problems in a way that's maybe not straightforward. I like to solve the problem rather than looking for an existing solution. And I get labelled now as a data scientist, whatever that actually means. So when I'm talking about research, it's often a process that looks something like this. There are formal specifications of the scientific method, and there are other life cycles that you might have doing experiments. But I thought about what most of my researchers would do, and most of my PhD students would do. And they often start with an idea, or a question, or a challenge to solve. So that could be the stereotypical hypothesis that you come up with and you run your experiments, or it could just be, we need to get a demonstration that shows how computer vision can be used to track pedestrians. All right, so it's something that we need to put together. Generally, we want to test or solve this fairly quickly in computing. So unlike some of the laboratory-based sciences where you might take, 2 years to grow your specimens before you do your experiments, computing moves fast. Right? You want to run your tests, get your stuff together, communicate your outcomes. And I think that's the other differentiator. You often need to demonstrate your solutions, particularly in my work and the research work that I tend to do. It's less and less common that it's okay to only have, say, a MATLAB simulation. We're looking to see something that's interactive, that's visual, that's communicating to your collaborators or to the wider public the solution or the question that you've been exploring. So in my case, that often involves lots of data and generally video data. So that puts some constraints on what I want to do. And then particularly if you're doing a PhD, you need to repeat those experiments with variations. You want to see if different features or different attributes are going to change the outcome. You want to let different machine learning methods take a crack at your problem. So you need to have something that's repeatable and reusable in a way that's not always the case if you've hacked up a solution to a problem. And then finally, as academics, we need to produce publications. So a lot of the outcomes then need to be turned into a report or some kind of publication on our work. So bearing those in mind, hopefully you can start to see where I'm going with this. Python offers a lot of solutions to these, right? Because of the richness of its libraries, right? Batteries included, it's the old slogan. It lets you do web-based frameworks really easily. It connects really well to other external systems for big data management. It has wide libraries for doing visualization, for putting together tables, for doing a lot of the basic core actions, but then you get all of the support stuff kind of for free, right? And that means that it's quite widely used, particularly within my research group. So just an example of how I used it in a recent project, and partly this is just an excuse to show this slide. So I mentioned that we work with Croke Park. So we had an initiative called How Loud is the 16th Player? So as part of our work, we have set a number of sensors into the stadium. They're connected to Intel gateways. They communicate with the Microsoft Azure cloud platform. And there are various things we do with that, number of projects we look at. One of the ones we wanted to complete was this idea of what was the impact of, or what was the influences on, how excited the crowd got. So we had a pair of microphones in the inside of Croke Park that give us the decibel levels. We don't record what people are saying, we just have measures of how excited they get, so how loud they get. So this particular graphic got put up on the big screen at half time. This one is from the replay in 2016. So it was the Dublin Mayo replay football final in 2016. And what we did was we looked at certain actions that we could observe, and then we looked for the peaks in the associated graphs that I was generating, and then we built this graphic. So you could see that Dublin entered and you get 100 decibel kind of noise. Mayo topped that by a whole 5 decibels, which actually isn't that much in the scheme of things, but most Dublin fans will get a little concerned about this. And the explanation to me is that the Dublin fans stay out in the pub and they don't come in, and so therefore they were just outnumbered, and that's the only reason that Mayo were louder. Dublin's first score got a nice big cheer, and then the 117 decibel was the loudest noise we observed that whole season. So that was the biggest noise. That's a bit like if I was to start up a chainsaw on the stage. That kind of level of noise would be what this room would be like. So this was great fun, right? Scientifically speaking, we had 2 microphones, right? And they recorded once every minute. So we could miss stuff, and maybe we didn't match things properly. I had one very stressful match where the Dublin coach sent the team on at the same time as the opposition, so I didn't get a clear separation to analyse and observe my data. So I was a little bit annoyed with them. But as an experiment or a set of research, it enabled us to test that whole pipeline, from data being captured, sent to a gateway, put up to the cloud, and analysed. So that pipeline looks a bit like this. The data was encrypted and sent up over a back end to the cloud platform. I was able to do the analysis and create the graphic, and then that was emailed to the screen operator. It's a very high-tech solution in the end. So you can see there the microphone that was being used for that experiment. So that all sounds, very technical and latest and greatest in IoT smart technologies. This was the back end. So embarrassingly, that's my bedroom, because it's the only place in my house that I have a functioning television, and I had a few screens there and I was using that. So what isn't shown on those screens is that in the back end I had a Python notebook that was using the SQL connector to pull the data in real time off the Microsoft Azure SQL storage database that was being used, and then I could generate various graphs to sort of see things happening. Now we have a dashboard that's installed onto the Azure cloud platform that does the reporting normally, but I needed to drill down a bit more specifically. So having a programming interface enabled me to ask questions more quickly and to see some of the details faster for my specific need. So that was the result of that. Very successful, very nice. And then we got the data afterwards and we started to look at the patterns and the analytics, and we discovered something a bit weird. So again, pulling the notebook down, I was able to graph this particular match, and you could see I've marked the Mayo goal, the record that we had. But one of the things that was quickly obvious when we looked at this is, why are there gaps? This was a little concerning because there shouldn't have been gaps. There should have been one number for every minute that we were recording. And so this was curious, and as scientists, things that are curious are what excites us to investigate. So we started to look further into this, and because we had all the data already in the notebook, it was in data frames, it was really easy to just try different visualizations, to do pure exploratory data analytics to try and spot what was going on here. And by looking at this one, this is the packets received per hour, we could start to see that there's a very clear degradation of, let me see if I can do this, there we go. Very clear degradation of the results around the time that the match was happening. So this is a red flag, and oh, something's not quite right here. So we looked at it in a different way. We split we had 3 microphones, we had one outside as well. The one outside didn't work for the whole day, so we discarded that from our analytics. But the 2 inside, we could see they were fine pretty much all the rest of the time except the match. So what would be different about match time? Fairly obvious answer to that one. Yeah, 82,500 people in the room. 82,500 people, most of them whom have a mobile phone, trying to do some connections. We're going, aha, we have an issue here. So this is part of why we do this research project, because we want to discover these problems and then come up with suggestions or ways of other people installing systems that avoid them having this problem. So what was really interesting though is it pretty much completely cut out at half time. We're like, well, why? It was very sharp. Why was it so bad at half time? And we looked and we thought, okay, maybe it's everybody's gone on to social media, or everyone's now logged on to check the soccer results, or something else. They do this at half time, that must be different. And so we actually published a paper on this. and we went to a workshop called Failsafe, and it's about disasters in IoT projects. So other people had sensors eaten by cows, they had sensors blown away in hurricanes, and I had warned people using mobile phones. So there's a more impressive disaster stories, but it was very interesting to be part of. Now, actually, the final conclusion we came to consulting with experts is it's more about the temperature differential. So the communication between the microphones and the gateways was via Zigbee radio waves, and they apparently are quite sensitive to changes in ambient air temperature. And what actually happens at halftime is everyone gets up to stretch their legs, they go and stand around at the empty spaces at the top of the stands, and they go down behind the stands to get their food and drink. And those empty spaces at the top are where our sensors are deployed and where our radio receivers are. So what we think happens is that the ambient temperature at half time has enough of an increase because all these warm-bodied people get up and walk around to cause that really sharp disruption. So Python was used in the back of this, and it meant that we could do stuff faster, we could generate these kind of graphs more quickly and go and talk to the engineers and the other partners to try and get a solution for that. So really what we have is something that is an excellent replacement for the old-fashioned lab notebook. I meant to bring mine and I forgot because I hardly ever use it. So I have an official hard-backed laboratory notebook that I should keep my notes in. But most of the team, well, you might use paper notebooks for note-taking. A lot of our experimental records are now in things like Jupyter notebooks. So a number of my PhD students keep excellent records of their experimental work, and they use it for things like generating the mathematical formulas that have to go into their thesis, and for keeping track of sets of experiments. Now I've got some of these, but they're not terribly interesting to show you chunks of Python code if I don't run them. So I have a few screenshots to prove that they're legitimate notebooks, but what these offer is really this repeatability and exploratory options that a static system doesn't. And this is becoming even more so now that things like the Google Colab is running so that you can execute your Python notebooks in Google Drive, and being able to use Git and have them render properly in a Git repository is really helpful for communicating with your supervisor because you can keep that kind of thing up to date and I can track what experiments that you've been running. And that enables all these sorts of graphs. This is from one of my PhD students, Camille Balas, who's doing really interesting work looking at the inside of deep neural networks. So for those of you that know about those, they're these really massive collections of numbers at their heart that are doing amazing work in computer vision. They've completely changed how well we can recognise objects and how well we can classify input. And Camille is really looking at what is happening to those numbers inside the network. In particular, how can we get those networks compressed enough to run on things like mobile phones or gateway devices or different systems, because ordinarily they need a GPU, so they need fairly beefy computational ability. So she is able to do these sets of experiments. She has a lovely table at the top that you can use to navigate through them, and she keeps track of all the different attributes or variations that she changes. And then she was able to generate things like these animated GIFs from her Python code, and this shows the gradient of change in the numbers in the different layers of the network. So it's quite hypnotic and kind of pretty, but looking at it was actually really, really helpful, because the thing with neural networks, the criticism people have of them is they are a black box. Really hard to know what's going on inside them. So visualizations like this, they're not perfect, but they do help us to direct questions in the right way. So you can see, particularly in the top one, very clear striations, right? Those stripes that run across horizontally. And that is interesting for us because it means that in some cases, the values for those layers are being fixed really early in the training phases and then they're not changing. So why is that? Is that because they're really critical and they stick to those numbers because it's the most effective, or are they really useless and therefore they just stop changing because they have no impact on the final results? So this sort of thing, in years past, would have been quite complicated to build these visualizations. We can churn these out. We can make a small change in the experiment, rerun it in the notebook, and generate one of these as our output, which gives us a much faster appreciation. Camille will often come back the next morning after I've had a question for the day before with a visualization that answers that question. Now, even even a year ago, 2 years ago, when I've had other students, that would be a week's work because you'd have to go off and run your binary code, you get your outputs, and you have to go and import your outputs into something else, do the crunching, import that into something else to get your GIF outputs, and all of that would add to the time. So that's really a summary of some of the stuff we're doing in the research field and how Python is informing some of that. So just a quick talk about how that then applies to data scientists. So I said I'm trained as a software engineer. So I tend to approach data science problems like I'm writing a computer program. So I will think about the basic building blocks of programming that I'm familiar with, the for loops, the if statements, the list comprehensions, and I will try and solve it like that. And when I'm lecturing the undergraduates in data science, I warn them about this because they're also studying computer programming. But as a data scientist, you're part of a much bigger ecosystem. And one of the big questions that we try and train people in is, if you're putting a lot of work into extracting that piece of analysis, or you're writing a lot of code to convert that data into another format, just stop for a moment and ask yourself the question, is this something other people are likely to have to do, or is it really unique to my situation? If other people are likely to have to do it, almost certainly one of the data science libraries like Pandas has a faster, more efficient, more flexible solution. So that's a real shift in how you approach data science. And I throw this graphic up because it's a commonly asked question, what is data science? And really it's this intersection. It's programmers who know more mathematics than those with computing degrees, and mathematicians that know a lot more programming than those with mathematics degrees, kind of glued together with this domain experience and analytics tools. So the sort of tools that we would teach in our undergraduate and master's courses really covers this range. So I tend to reach for Python as my examples because it's what I'm used to. I have a fellow lecturer who is my mirror. She reaches for R because that's what she's used to. And our master's students find that slightly amusing because she spruiks R and I spruik Python, and they get the best of both worlds. So really it works quite nicely. But on the side of the slide here, you can see a fairly generic pipeline for data analytics. So similar to the cycle for research, there's a lot of stuff in here that would ordinarily require lots of different tools. But what you can do with the libraries and being able to record things in the notebooks is you can operate at each of these levels in a very coherent way. You can produce something that you can take to a client, that you can take to a boss, and that you can justify. I've seen on the schedule there are some fantastic talks around things like open data science, which is critical, right? Particularly as the wider public needs to be consulted and educated on what their data means and what people are doing with that data, and how people can mislead with statistics and data analytics. Having processes in place for professionals to be able to document and make their work very transparent is something I would be a really big advocate of. I think that's a critical thing for us as a community to be supporting. So when the new Masters in Data Analytics come into my course in DCU, I ask them what their background is because they come from a really wide area. And one of the questions on that survey is about their Python experience. Are they a novice? Are they a beginner? Are they intermediate? Or are they advanced? So I just thought it would be interesting to see over the last 3 years, which is how long I've been teaching this course, what the differences in experiences has been. Now, I will caveat this as a true data scientist should. These are not significant in any sense. It's a very small sample set. It's over a very short period of time. But you can see something fairly interesting. The first year I ran this, 60% of the class had no experience in Python, so none at all. And so I ran some remedial labs where I gave them the basics of Python. The second year, so 2017, that had dropped to 40% of the class had no experience of Python. And then this year, only 20% of the class hadn't had any experience of Python at all. And correspondingly, you can see that there's an increase in those that have created some kind of small project or have some exposure to Python, and also an increase in those that have created several projects or implemented a large project in Python. So it's too early to tell. But this is the kind of process I would expect to see continuing over the next few years, particularly as we're starting to get undergraduates who've been introduced to Python, and we're starting to get people from the computing leaving certificate that have been introduced to Python early on, and that information is going to continue to flow through. Okay, so wrapping up quickly, just a brief comment on the undergraduates at DCU. I consulted with a number of people when I was asked to prepare this talk, because I was going, well, what should I talk about? And I went and asked Dr. Stephen Blott, who's the head of the Computer Applications program at DCU and who teaches the introductory course in semester 1 to the first years about Python and programming. So I said to him, well, what's been the experience in the 3 years that you've introduced it? And he said, well, one of the important things that you should remember is that we teach computer programming, just happens to be using Python. So that's an interesting distinction. That he doesn't consider himself to be teaching Python per se, but certainly in the first semester he's teaching computer programming, and Python is just the medium for that. But he said one of the major advantages that he's seen in this is that students can achieve results very quickly. So unlike a lot of the other programming languages where you have to set up scaffolding and compilers and all the rest of it, you can get results with Python really fast. So for nervous beginners or people that have never touched this sort of thing before, it's of huge benefit. And I suspect that's one of the major reasons that it's often used as an introductory language. So really this is very encouraging for new learners. So that's great. There is a dark side of that, of course, right? So part of that comes about that Stephen has implemented this online platform to mark students' programs. So they write a program, they upload it to a platform called Einstein, and it tells them if their code is correct or not, if it runs. But what Stephen found students were doing is they just keep throwing programs at the platform until they got one that worked. So they weren't testing it locally, they weren't really thinking about what they were doing, they just kind of kept, a bit like the monkeys writing Shakespeare, writing program code until they got one that got them the green tick. So he implemented this thing called a sick mode. So what happens if you submit an answer that's wrong and you do this over a certain threshold of time, your screen gets a big red thing on the side and a few other inconveniences. You have to wait a few seconds before you can upload things. You might have to answer a simple mathematical sum before it will let you upload. So he set it up that you want to avoid sick mode, and people can see that you've gone into sick mode because you've got this red square on the side of your screen, right? So peer pressure, it's a great thing. So all of that was put in place to try and help them to think more about what they are writing as programs, right? It's not a magic box. It's not something that you just keep pushing buttons until the lights change to be the pattern that you want. But it's something that you have to put thought and consideration into. So really, what he said is that students were thinking of computer programming like magic. Right? A bit like you follow a certain set of chants, you move your fingers in a certain set of ways, and stuff happens. And I was teaching Introduction to Operating Systems for a couple of years, and I found it was similar, that students didn't have that understanding of things like compiling, of pointers, of memory management, because Python protects you from all that, which is lovely. But at a certain point, we have to break that protection and bring them into understanding of that. So one way Stephen does that is, for example, he doesn't teach for loops in first semester. He makes them use while loops. And to get more of an algorithmic understanding of what's happening underneath the back of the screen, so to speak. So that's just a few quick comments on some of the experiences at DCU. So, like any good lecturer, I have to have a summary slide. So just to summarise some of the points from what I've been talking about here. Python has a great deal of advantages as a research tool to support the work that we're doing within the research group that I am, but also as a teaching tool, and that's evidenced by its increasing popularity. Part of that is because you can rapidly develop really quite powerful stuff, but in particular for the data analytics aspects of it, it's a very structured method. Right? This still relies on the experimenter or the researcher having discipline, writing proper notebooks, but the framework is there to support good practice in that. It's really becoming the new lab notebook for digital experiments. So as opposed to the paper copy that they would still use in a lot of cases, it's moving towards that. That raises interesting legal questions, because traditionally the lab notebook is your evidence of your development work, your protection against accusations of plagiarism or intellectual property infringement. To my knowledge, that's not yet been tested in terms of something like a Jupyter notebook, and how that might work in a legal framework. It also gives us the ability to present and share open scientific experiments. So it's fabulous to browse GitHub and see people's academic publications have put all of their code and all of their data up for other people to reproduce their work. And that is how true scientific progress is made. So that's an excellent advancement. And particularly for us, where we want to do stuff that has really interactive demos, it gives us a lot of that for free. So it's a really useful tool in that sense. No pros without cons. There is a concern that, particularly if it's your first language, it becomes a bit of a crutch. Right? You're used to print hello world and not having to think too much about some of the other stuff. And so the way it's taught needs to be carefully considered to ensure that there is computational thinking, that there is an understanding of computer systems that are going to make people better programmers. One of the disadvantages is there is more than one way. So helping students to understand good practice and not just, and I'm very guilty of this, hacking it until it works, but actually thinking about what is a good way of doing things. Some of that comes down to what is the difference between a programmer and a data scientist? Well, for me anyway, who's probably trained more as a programmer, it's about making it work, fixing the problem. I know how to break things down into algorithmic ways. For a data scientist, it's about having a deep, broad understanding of the available tools and libraries and knowing which toolkit to reach for in a particular situation. So it's a slightly different level of understanding. An open question perhaps for discussion in the break is, do notebooks compromise coding style? So if you're not having to build classes and functions, and you're not thinking about importing modules in the same way that you might have traditionally built a standalone .py script, do you think that is a positive or a negative impact on your actual coding style, if there is such a thing? And a final comment came from one of my European collaboration partners when he asked me if I knew of any way to package Python code so that it could be obfuscated and not reverse engineered. Because he works for a commercial research centre who are doing tremendous work and pulling this stuff together. They're writing it in Python, but they can't give it to their clients like that because they could see all the magic, and then they don't have a defensible commercial product. So that's been a question that's come up many times in the Python community, and it's still being raised by people in that area. So particular thanks to Dr. Stephen Blott for his input, but also to Dr. Jian Zhang, who's part of my research team, and again Camille for providing me some of their work, and a number of other members of Professor Noel O'Connor's research group at DCU. And thank you very much for having me. It's been an unusual talk to put together, and I hope some part of that has resonated with you and you're looking forward to the rest of the weekend. Thank you very much.